Welcome to the last lecture of nonlinear modeling. Today we're going to talk about more advanced finite element methods for the modeling of quark propagations. We'll first do a recap of what we've covered last week, some of the materials. Then we'll mention about remeshing, non-local methods, and the very famous extended finite element method, followed by the phantom node and the floating node. Last week we've talked about fracture. We know that in fracture we have three different modes corresponding to peeling and the two sharing directions. And we have talked about the cohesive element, which is used to model quark propagations. It can be used to model both brittle material and the tougher materials. It is very versatile, but we need to know in advance where the cracks are going to appear in order to use this type of element. And a workaround is to smear this cohesive element within the bulk element, such that we represent the effect of having this cohesive crack with the stiffness degradations on the constitutive tensor at the bulk element integration points. However, this method suffers from the mesh bias issue, which means that now we are no longer modeling a sharp crack, but it is more like a smeared band of filled elements, and the directionality of a crack propagation is very much biased towards the direction of the mesh. So if we have a mesh aligned along this direction, then most likely the crack would propagate also along the direction of the mesh. So today we are going to talk about methods to overcome this mesh bias. And the most traditional, most straightforward way is to simply do a remeshing. We basically delete the elements around the crack tip, then remesh the region according to the new crack geometry, so that the elements always conform with the crack geometry, and we always represent a sharp crack. This method applies to all cases. It's a generic, but it is, however, quite tedious to implement because you need to delete original elements and then you need to form new elements. These elements would have different node numbering and different connectivities. So when you have just a few cracks, that's still doable. But when your number of cracks becomes quite substantial, as in the case of composites, then it becomes problematic. You have to think about updating the element connectivities, a number of elements with respect to each crack propagation and each crack appearance. And in the case of composites, you could have hundreds of matrix cracks. And you have many plies also. Together with delamination, it then is not very practical to apply remeshing there. Now, we need to come up with more efficient and also effective ways to model crack propagations within materials such as composites. And the crack propagations needs to be independent of the mesh construction. One way is to use the so-called non-local damage model. Traditionally, when we use the smear crack model, we have the stiffness degradation applying on the constitutive tensor, and this degradation or damage variable is a function of our strain, and this strain, which is mixed mode equivalent strain here, is evaluated locally at this element integration point. So this means that the damage variable depends on the strain in the local element. For instance, for constant triangular element, we have a single integration point in the middle, and the damage within this element depends on the strain in this local integration point. Now the non-local model is to replace this dependency on local strain by a dependency on a non-local strain. This non-local strain is a weighted average over a region. So this is no longer just evaluated at a single integration point, but evaluated over a domain, over a region, over a certain radius, and the different integration points within this region all contribute to the evaluation of this term, but their contribution carries a different weightage. So then you can construct this weight function. Typically, if you evaluate the damage variable at a location x, for instance, at this point, the strain evaluated at this point would carry a higher weightage than somewhere here, for instance. So you can design sometimes a Gaussian type of weight function where it peaks at this point, the weightage is highest here, and then gradually decrease to 0 towards the boundary of this region. So this is a non-local damage model. And the advantage of having a non-local definition of strength for the evaluation of a damage variable is that now our evolution of damage variable is less dependent on the underlying mesh, because you have a so-called fixed radius, and regardless of how your element is designed and aligned, as long as your radius of this region is large enough, you have a pretty much unbiased evaluation of your damage variable. So this, using non-local method, it is possible to overcome the mesh bias that appears in a local method. Recently, a very popular approach is to use the so-called extended finite element method. And in the extended finite element method, the elements are enriched with additional degree of freedoms and additional interpolation functions. For instance, an element in the finite element method is composed of a selection of nodes. You have an element defined as a nodal connectivity matrix. Each node is allocated with certain sets of degree of freedoms. In a standard finite element method, you will have one set of degree of freedom for each node. So this set would contain, in two-dimensional case, the displacements along x and y directions. In the X-FEM with a certain enrichment function called Heaviside enrichment function, we double the degree of freedoms on each node. So now each node has two sets of degree of freedoms. And what happens is that when the crack appears, we make use of these additional degree of freedoms, 5 to 8, to form a separate interpolation over the element domain. So we have the original interpolation. The displacement solution here would be the same as the standard finite element displacement solution. We have this additional interpolation. So basically, our displacement interpolation on omega is composed of two parts. The first part is a standard finite element interpolation using the standard shape functions, and the second one is the enriched interpolation using this enriched shape function, h. Now this h is simply a step function. It equals to 1 when your material point lies within one domain, above the crack, for instance, and equals -1 when it's below the crack. So this way we can make use of this interpolation function to represent a displacement discontinuity across the crack surface. So basically, whenever a crack appears, you are physically creating 4 additional nodes, in fact. And you need these 4 additional degree of freedoms together with this continuous interpolation function to represent the jump of the solution across this crack surface. And in X-FEM, we also have a second type of enrichment, which is called tip enrichment. This is more relevant to linear elastic fracture mechanics and for isotropic materials. In linear elastic fracture mechanics, for isotropic materials, we have an analytical expression for the displacement fields near the crack tip. They are composed of these basis functions. The idea is to make use of these basic analytical basis functions to enrich interpolation space of a finite element near the crack tip, for instance, this element, so that the overall displacement interpolation within a certain element in X-FEM is composed of 3 parts. We have the standard finite element approximation. We have the Heaviside enrichment term, which we described in the previous slide. And we also have the so-called tip enrichment term. Here we make use of this analytical tip enrichment functions, and we allocate additional degree freedoms to interpolate these shape functions. So the basic idea is to make use of available analytical information on the displacement field near the crack tip to enrich our finite element shape functions. However, this analytical tip enrichment is not always available for generic material. It is available for isotropic materials, but for anisotropic material, for instance, for composites, is generally not available. A popular variant of the extended finite element method with Heaviside enrichment is the so-called phantom node method, or sometimes called Hansbo's method, because it is Hansbo who invented this method. Similarly, as in the XFEM, we have the element defined as a selection of nodes, and also we have additional degree freedoms. Here we have instead of 4, which is the usual case with standard finite element method, we have 8 sets of degree freedoms. Conceptually, however, there is a difference. We have the original 4 nodes, and also we allocate 4 so-called phantom nodes to the element definition. Now each node is still the same node as before, which means that each node has the same single set of degree freedom allocated to it. We make the difference between real node and phantom node. A real node is the node that appears from the beginning when you create the input file, when you create the geometry and you mesh. You generate the real node with the nodal coordinates and the default degree freedoms. Then you create the so-called phantom nodes, which is just a double of the existing real nodes. Now, when a crack appears, what happens is that you make use of both the real nodes and the phantom nodes to form 2 sub-elements. Each sub-element has only part of the domain being active, meaning that only part of the domain has the real material. The other part, for instance, here is empty. Similarly, here you have only omega A having real material, and this part is empty. The effect is that now these 2 elements are independent elements, so they have separate interpolation of solution, displacement solution, over these 2 separate element domains. And when you localize the solution on the respective material domain, active material domain, then you have 2 separate displacement fields, which can very well be discontinuous across this line of separation. In other words, mathematically, the displacement field is represented by this expression. You have a sum of 2 parts, and this part means that you only have the material active on omega b, and h omega b equals to 1 in omega b, and equals to 0 when x falls outside of omega b. Similarly here, h omega a means that it is a step function which is equal to 1 when x is within omega a, and 0 when x falls out omega a. So these h Heaviside step functions serve to localize your solution u as E1 and u as E2 onto the respective active material domains within these sub-elements. And then the solution over the element domain SE1 and SE2 are formed using the standard shape functions, the N1, N2, N3, and N4, with both real nodes, real degree freedoms, and phantom degree freedoms. A1, A2, they belong to the real node, and A7, A8 belongs to the phantom nodes. Similarly here, A5, A6 belong to the phantom nodes, and A3, A4 belong to the real nodes. In this way, you have a very simple method to represent this continuity in the solution field by forming 2 sub-elements. Conceptually, it is simpler and more straightforward, in my opinion, at least, than XFEM. In XFEM, you work with enrichment functions, while in the phantom node method, you simply subdivide the original element into 2 sub-elements. The 2 solutions are actually equivalent to each other. You can see as a schematic drawing that you partition, when the crack appears, you partition the original element into two sub elements with each with only part of the domain being active. Then each sub element has its own interpolation. You use your Heaviside localization function to only integrate on the sub elements, on the subdomains which contains material, and then you assemble the two back into the original element domain, and naturally you would see a jump in the displacement field when there is a crack. You could make use of this jump in the displacement field to form a third subelement, which is a cohesive subelement, in between to model a cohesive crack. This is entirely possible. This method is very convenient, and this is in fact the method that is implemented in Abaqus for the modeling of crack progressions. Although there it's called XFEM, but in fact it is the phantom node method. In terms of computational architecture, let's say you have a global mesh, and you have n elements in the mesh, and upon a certain loading, element I starts to have a crack. What happens with the smear crack approach is that you degrade the stiffness properties of element I, and you keep the original architecture the same. So there's no change in terms of element connectivity, number of elements, and assembly procedure and the global system equation. There's no change there, except that now the stiffness properties of this element are degraded according to a cohesive law. In remeshing, however, you delete the original element I, and you replace with a bunch of new elements. So these elements would have different nodal connectivities as the original element, and of course you have more elements in total, and your system needs to be adaptive enough to take in all these new elements. Your size of the problem would grow larger and larger as you have more and more elements. In XFEM, when the crack appears, you enrich the interpolation of this element I. So the degree of freedoms of this element are already pre-allocated before the analysis. You don't have the growing in size, as in the case of remeshing, but you do change the interpolation of your solution around the analysis when the crack appears. So before any crack, this element I is the standard finite element, which use the standard shape functions for interpolation. After crack appears, this element I changes and includes all these additional interpolation functions, such as Heaviside enrichment and crack tip enrichment, so that the solution field changes to better represent the actual displacement field near the crack. In the phantom node method, the approach is that now you add a sublayer underneath your original element, where you have two sub-elements, and you perform the integration on the sub-element level, and then you assemble these two sub-elements into your original element I, and then you assemble again to the global system. So you have one more level of hierarchy in the phantom node method. So this is an overview of the difference at a more abstract structural level.